I'm involved with the organization of this very interesting conference, but just concerning the invitation of speakers. So I must be very grateful for the hard job to Olga, Jana, Ivan, and Oleg. Okay, I can start with my talk. It concerns a paper in collaboration with my colleagues Niccolò Drago and Sonia Mazzucchi. This paper concerns actually a long-standing problem arising from physics. This is a possible solution, at least at mathematical level. Okay, this is the summary of the talk. In the first part, I will discuss the so-called linear structure of observables in quantum physics. In the second part, I will illustrate a solution of some problem discussed in the first part, first in a toy model and next in a general formula. And in the third part, I will discuss how to apply the result to some other problems in quantum physics. And if there is sufficient time, I also discuss some interplay with Feynman and Feynman-Katz integral formulas. And finally, I will present some conclusions regarding the physical interpretation of our formula. Okay. I would like here to summarize some elementary facts in the formulation of quantum theory. Maybe you know that there are two main approaches. One is based on the algebraic formalism, the C-star algebra, and the other, the older one, is relies upon the first formalization of quantum mechanics, quantum theory, due to essentially to von Neumann. In this case, I will use this formalization. Observables are self-adjoint operators on a certain Hilbert space. Actually, they are self-adjoint operators affiliated to a von Neumann algebra in a complex Hilbert space, and states on the system described in this Hilbert space are statistical operators, also called density matrices, which are positive trace class unit trace operators. Okay, I will only consider this second approach, the older from the historical point of view, because in this approach, it is possible to justify the idea that observables are described by self-adjoint operators. Okay, from the point of view of von Neumann, a quantum system is associated with a Hilbert space, a complex Hilbert space, and with its lattice of orthogonal projectors. These object as the mathematical structure of a non-Boolean orthomodular lattice. The physical interpretation of the elements of the lattice, I mean the orthogonal projectors, is the interpretation in the sense of elementary observables. And a projector is, from the physical point of view, an elementary question on the system, which has only two possible outcomes, yes or no. You know that in quantum mechanics, there are observables which are not compatible, which means that it's not possible to measure simultaneously both them. For instance, the Heisenberg principle is a consequence, a physical consequence of this fact. And in von Neumann approach, compatibility of a couple of elementary observables, yes, no observables, corresponds to the commutativity of the corresponding projectors. This is the way to construct, for instance, the quantum logic by Birkhoff and von Neumann and so on. Okay, a state in this, a quantum state in this framework is nothing but measure, probability measure, defined on this lattice of elementary observables. So I will not enter into the details, but this is a map associating each projector with a number in the interval 0, 1, which represents the probability that this property is found to be true if I perform a measurement of it on the system. Let's assume the simplest case where the lattice of projectors coincides with the full lattice of orthogonal projectors in the Hilbert space. This is a standard situation in physics. Okay, in this case, a famous theorem, the so-called Gleason theorem, proves that if the space is separable with dimension different from 2, then the states are completely described by statistical operators. I mean, trace class operators positive with trace 1, and the probability that a proposition, elementary proposition, is true takes this form. The trace of the operator associated with the measure multiplied with the proposition, the projector. Okay, extreme measures are, in this case, represented by one-dimensional projectors, and the function, if the space, Hilbert space, is an L2 space, the function entering the projector, taking the function, this function normalized, is the so-called wave function of the system. Okay. It is, in this case, it is also possible to define general observables. From this perspective, a general observable is a collection of elementary observables labeled by set in the Borel family of sets of the real axis. The meaning of this projector is the value of the observable associated with this family of projectors belongs to E, to the Borel set E, if obviously, if I perform a measurement on the system. Okay, using a standard result of quantum logic, I will not enter into the details. It's possible to prove that this map actually is a sigma algebra homomorphism, or from the point of view of functional analysis, is a so-called projection valued measure. So I can integrate with the standard spectral machinery, spectral calculus machinery, these families of projectors, and I obtain a Selfadjoint operator. The support of the measure, this family, is exactly the spectrum of the observable. All the procedure can be reversed, so there is in fact a one-to-one correspondence between Selfadjoint operators and families of projectors labeled on the Borel set of the real line. Okay, this is the reason why observables in quantum mechanics are represented by Selfadjoint operators. Okay, can go on. Okay, when one reaches this more abstract level where observables are not families of projectors but are Selfadjoint operators, he or she discovers that this family of new operators enjoy some new emergent structure. In fact, we can combine linearly a couple of Selfadjoint operators in this way, and if the coefficients are real, we obtain also a Selfadjoint operator. So on the ground of the previous achievement, we have to conclude that this object is also an observable of the theory. I can also construct another observable using this sort of product, which is called the Jordan product, which is not associative. The point is that I want that this operator is self-adjoint. Okay, so it seems that once we pass from the logical point of view based on the projectors and elementary observables, when we pass to the level of self-adjoint operators, we have at least two problems, actually is the same problem, which pop out from a physical point of view. Here there is the same problem stated in terms of physics or mathematics. Let's start from physics. Suppose that A and B are observable. So I have some physical instrument which is able to measure A and another physical instrument which is able to measure B. So I perform this real linear combination. I should find, since this is another observable, a physical instrument which is able to measure this linear combination because this is a self-adjoint operator. But if A and B are not compatible, in general, there is no way from basic assumptions in quantum physics to construct, to define this instrument using the instruments we have associated to A and B respectively. From the mathematical point of view, the same issue more or less can be stated this way. Suppose that this is the family of elementary propositions associated with this observable. Yes, no, elementary observable. This is the other family. Is it possible to construct the elementary observables of these this composite observable using or out of the elementary observables associated to A and B, in case A and B physically are, from the physical point of view, not compatible? In general, there is no answer to this problem. This is a big problem, especially for experimental physicists, because it is usual. We faced this problem, Sonia and I, dealing with a group of physicists dealing with photonics. We had a couple of observables. We constructed this linear combination in general, and we discovered that we weren't able to indicate the instrument to measure this new observable. Okay, there are other technical problems in the general case when A and B are unbounded operators. Okay, but I will not insist on these technical problems. I only say that in case A and B are generators of some representation of some Lie group of symmetries of the problem, in this case, it is in general possible if we are able to measure A and B, or if we know the PVM the family of elementary propositions associated to A and B using the group, the action of the group on the generators. Is it sometimes possible to construct the elementary observables associated to this new observable out of the elementary observables associated to A and B? But this is a very particular case. It's not possible in general. Okay. Here exactly is the point where semigroups enters the issue. We found a general answer, at least from a mathematical point of view, to the considered problem. I illustrate this solution using, first of all, an elementary model where the Hilbert space is finite dimensional. So in this case, consider self-adjoint operators, A and B, and we want to construct this function of this operator, so in particular, this operator itself, using the elementary observables associated to A and B. So the spectral measures of A and B. In this case, the spectral decomposition, this elementary case, the spectral decomposition of a function of an operator takes this form. Sigma is the set of eigenvalues of A, F is any function, and this is the projector onto the eigenspace with eigenvalue lambda of the operator A. So the central tool in our result in this elementary case, but it takes a fundamental role also in the general case, is the total formula. It is written here. Now the topology of the convergence is, it doesn't matter because we are in the finite dimensional case. And our formula is this one. So the left-hand side is defined this way, replacing A with this self-adjoint operator. A and B are real, capital A and capital B are self-adjoint. So this is a well-known object, but here in this formula is constructed using the spectral measures, the family of elementary propositions of A and B. This formula is very suggestive because you see that here the average value of this linear combination of eigenvalues of the operators A and B takes place. And we have to consider the limit for n tending to infinity. Okay, so this is in practice our formula. I sketch the proof in this elementary case because there are no problems with domains and topologies. So using the standard spectral theory, we can write this function using its inverse Fourier transform and the spectral calculus. Exactly here, we can use the Trotter formula. Now, each of those operators, actually they are one parameters group of unitary operators, can be expanded using the spectral expansion. So using this formula, and here the corresponding spectral measures take place, and inside this integral I can use again the standard Fourier transform. So finally we obtain this formula. Very easy in this elementary case. Okay, actually the difficult job is to extend that elementary idea to an important general case physics, where A and B are not bounded, because the relevant observables in physics are not bounded self-adjoint adjoint operators. And this is our main theorem. Suppose that A and B are self-adjoint operators on a separable complex Hilbert space. And suppose that this linear combination where A and B, small a, small b, are real, is essentially self-adjoint in the intersection of the domains. And this is the most easy hypothesis to for the validity of Trotter formula in the unbounded case. In this case, the previous formula, this one, is also valid for unbounded operators, provided this sum is transformed into an integral. The point is to make a precise, to give a precise meaning to this integral, because in general, those spectral measures don't commute, so this is not the so-called joint spectral measure, which is not defined. The class of functions we use here is a quite comfortable class of functions in physics. This is, in this case, the Banach algebra of the Fourier transforms of complex Borel measures in R. This family contains the continuous bounded function, the Schwarz space, the test function space. Sorry. Okay, the limit is computed using the strong operator convergence. Also in this case, because the Trotter formula is valid in general in the strong topology of operators. I will not enter into the details, but I would say, I say just something about the construction of this measure, which is quite similar to the construction of the Feynman integral. The idea is to define this operator using a weak topology. So we first try to define not this operator, but a quadratic form related to this operator. We must use a regularization, I mean a class of finite dimensional orthogonal projectors tending to the unit identity operator strongly. And this is the reason why the space must be separable. Okay, so we define a measure for each value of small n, and our so we define an operator, this operator, which is the unique operator which satisfies this identity, where this measure is defined. This operator doesn't depend on the choice of the regulator, and this formula becomes the standard, the analog concerning the joint spectral measure when the operators A and B commute, the spectral measure commute. There is a problem which is identical to the analogous problem with the Feynman integral, that this object cannot be associated with a measure because the total variation diverges. Sonia told something about this problem in the previous talk. Anyway, so this operator is well defined, and this operator here is the strong limit of this family of operators. Okay, the formula permits in particular to, well, yes, to construct the spectral measure of the family of elementary propositions associated to this operator, which was the main problem considered at the beginning of my talk. And it takes this formula. This is a regularized version of a, how to say, a function, characteristic function defined on this set. It holds 0 outside this interval and 1 on this interval. The further regularization is necessary because the function used here must belong to the family of our family of functions, which is made of continuous functions. Okay, the formula permits to obtain other results. In particular, we can produce an practical representation of this Jordan product. The idea is very simple. If A and B are bounded or are bounded below, for instance, you can change the function f outside this domain or this interval or the analogous semi-interval when the function, when A, B, and bounded below. So in this case, we can extend the family of function which can be used in our formula. For instance, in the case of bounded operators, using generic smooth functions defined on the whole real line. And we obtain, for instance, this formula for the Jordan product. Again, you see here an average value of the eigenvalues of the elements of the spectrum. And it is also possible to extend the formula to polynomials symmetric in two variables. So it is possible to associate to polynomials an operator which is function of two non-commuting operators. This is the starting point for a quantization procedure, different from, for instance, Weil quantization or Berezin quantization and so on. I'm almost finished. There is a nice interplay of our formula and Feynman-Katz integral formulas, because if you consider, for instance, this couple of operators which are not, which don't commute, evidently, momentum and position, and we consider this function of them, this is the standard evolution operator of the harmonic oscillator, but here we can insert any potential, suitably regular potential. So we can use our formula, and this matrix element computed with our formula, we insert those vectors here in the measure. This formula is exactly the formula of Feynman integral. So it can be recast into this formula, which is the one of the Feynman integral. The same happens with the Feynman-Katz formula, using the semigroup instead of the group. This bar denotes the closure of this sum of operators, because this operator is only essentially self-adjoint, and we need a self-adjoint operator, which is the closure. Okay, I'm finishing. From the mathematical viewpoint, everything is clear. We have a machinery which is able to produce a function of a linear combination of operators in terms of the spectral measures of the operators. The physical meaning of our formula is not so clear, and it deserves further investigation. Here there is some idea to try to interpret the formula. This is, physically speaking, if f is real, is the quantum expectation value of this observable when the pure state is represented by this wave function, this pure state of the system. Using our formula, we obtain this expansion. Okay, here, this term has an interesting interpretation. It is an object in the so-called consistent hysteresis approach to quantum mechanics. Is a conditional quantum probability. Is the probability to obtain this sequence of outcomes if I measure, if I consider an alternate measurement of B, A, B, and capital N times. But this formula includes also this last part. In some sense, it represents a quantum interference. So even if this term may have a classical interpretation, is a conditional probability, these terms is completely has a complete quantum nature. In fact, it disappears as soon as A and B are compatible, if they commute, if they can be inserted in a large maximal set of commuting operators, which is a classical object. So I can conclude here. So from the mathematical point of view, we obtained an interesting result, but the physical interpretation is not so clear up to now. Okay, I can stop here. Thank you very much from the presentation.
Thank you very much for your interesting talk. Let us thank the speaker.
Thank you.
Yeah. So are there any questions or comments?
I have a comment.
Yes, please.
There is a simple corollary of what I gave in my talk. You are here using quantum groups and expressing them in another quantum groups, but you can also do this expressing quantum in terms of classical.
Не видно ничего, Ваня. Да, не шевелись, так видно. Ага, прекрасно видно. Yeah, so this is a quasi-Feynman formula.
So this is a corollary.
Yes, but you use a stronger structure, the one of quantum group. You have a group. I mean, consider A and B. In general, you can expect that A and B are generators of some group, of a unitary representation of a group. It happens if and only if there is a finite Lie algebra, which includes the commutator of A and B. So you take A and B, the commutator, you obtain some operators. These operators in general is not a linear combination of A and B, but you can add further operators to A and B, and with this extended family finite of self-adjoint operators, you can also obtain the commutator of A and B. If this is true, but this is a very peculiar case, you can embed all the theory inside a unitary representation of a group. In this case, you have many other possibilities to, I don't know now which group you consider it, but in general, this is not the case. The unfortunate case is this one. You consider A and B. you consider a commutator of A and B, you obtain an operator C. If you consider a commutator of C, A, and B, you obtain another operator D. And finally, you obtain an infinite class of operators. In this case, there is no group which you can use to construct an overall theory which embeds everything. We consider this generic case, which is the standard in quantum theory. Okay.
Nevertheless, the formula which was shown by Ivan has also generalizations. We don't need groups.
Yes.
We can consider just families operators.
Okay.
Which are not approximations of something. So we
Chernoff
don't.
tangent. They may even not generate approximations themselves, just Chernoff tangent.
Okay.
Yeah, so this formula can be generalized, so one does not need to care about groups.
Oh, okay. Sorry, I heard the quantum groups, so I interpreted.
No, another quantum groups.
Okay, another idea of quantum group.
So this formula can be generalized to using Chernoff approach.
No, yes, I think so. Okay.
So other further questions or remarks?
The formula. Okay.
So
if you have some interest, Valter, I can make a photo of it and send you via email just now.
Yes, thank you very much.
So I have small remarks. So you have mentioned that this formula is related to some payment path construction of payment path integrals in the case of non-commutative configuration space. Have I understood properly?
No, it doesn't matter. No, okay. Let me focus on the statement. Where is it? Here. No, it is related with the standard Feynman. Sorry.
Standard Feynman path.
The standard in the phase space.
Okay.
There is no. The only non-commutativity may arise from the quantum nature, but at quantum level.
Okay, thank you. Okay, because I just wanted to make a remark that in the group of Smolyanov-Shogulidze, there was a PhD thesis defended several years ago where the Feynman path integral was constructed to the case of non-commutative.
But non-commutativity is described, for instance, with the Moyal product or something similar.
Well, I don't remember, but just the configuration space of the system was already non-commutative.
Okay.
I just so if it's somehow interesting, one can contact Professor Shogulidze, I guess was the supervisor, and yeah, I guess they have some results.
Thank you for the information.
Okay, so well, are there any further questions or remarks? Well, seems to be not to be the case. Then let us thank the last speaker and all the speakers of the section again. Thank you very much.
Thank you to you.
I'm very happy to have a section on Feynman path integrals. We had also a lecture on this on Monday. So yes, and it's a good idea to mix different communities. Sometimes people think that they do very different things, but actually there are many interrelations between them. So hopefully we will figure out some of them during this conference. Okay, well, so thank you.